Good morning. This is your stats sensei, Mr. Sensei, and this is our extra credit video for exam B. This is the fourth one, and we'll be doing problems 32 through 40 on it. So here we go. An independent research firm conducted a study of 100 randomly selected children who were participating in a program advertised to improve mathematics skills. The results showed no statistically significant improvement in math skills using alpha equals 0.05. The program sponsors complained that the study had insufficient power. So we're caring about power. Assuming the program is effective, so in other words, it really is effective, which of the following would be an appropriate method for increasing power? All right, so how can you increase power? Well, you can decrease the standard deviation. You increase alpha. You can decrease type 2 error. You can increase the sample size. A two-sided test instead of a one-sided test. No, that does not increase power. That decreases power. And here's why. The reason it decreases power is that with a two-sided test, instead of having all our area in one tail, which makes it easier to reject, we have the area divided by two tails, which makes it harder to reject. So that's false. Using a one-sided test instead of a two-sided test, true, that help. So that's true, but we're looking for appropriate. Use alpha equal 0.01 instead of 0.05. No, that makes it harder. That's completely false. Decrease the sample size? No. All right, increase the sample size. Increasing sample size is the best way to increase power. And so while B is technically correct, the best choice is increase the sample size. 5 estimators for a parameter are being evaluated. The true value of the population is 0. Simulations of 100 random samples each of size n are drawn for the population. For each simulated sample, the 5 estimates are computed. The histograms below display the simulated sampling distribution for the 5 estimators. Which simulated sampling distribution is associated with the best estimator? So we're looking for the best estimator. Well, the best estimator has to be centered on 0. Well, that helps because that one's not centered on 0. This one is not centered on 0. And this one down here is not centered on 0. So now we're down to 2. Well, once we have them centered on 0, and both of these appear to be centered on 0, we want the one with the smallest variation. Well, A has a larger variation. We like B because it has a smaller variation. So centered on 0, or centered on the true parameter, which is 0, which we are, and the smallest variation. Centered on 0, smallest variation, we like B the best. For number 34, a planning board in Elm County is interested in estimating the proportion of its residents that are in favor of offering incentives to high-tech industries to build plants in that county. A random sample of Elm County residents was selected. All of the selected residents were asked, are you in favor of offering incentives to high-tech industries to build plants in your county? A 95% confidence interval for the proportion of residents in favor of offering incentives was calculated to be 0.54 to 0.05. So basically as low as 49% and as high as 59%. So we're 95% confident the true mean or true proportion lies within this interval. At 95, the estimate of 0.54 is within 0.05. Well, 0.05 means it's going to be somewhere in that interval. I like this one. This looks pretty good. At the 95% confidence level, the majority of residents are in favor. No, we don't know that because 49% is included, which is not the majority. In repeated sampling, 95% of the proportions will fall in the interval. We never talk about the sample, so that's false. When we proceed in sampling, the true proportion of county residents in favor will fall in the interval. No. In repeated sampling, our method captures the true proportion 90%, so they said that wrong. In repeated sampling, 95% of the time, the true proportion of county residents in favoring will be equal to 0.54? No. We are 95% confident that it lies within this, or 95% of the time in repeated sampling, we will capture it. We didn't say that it would equal something. So the only answer that works for number 34 is A. Number 35. A group of students has 60 houseflies in a large container and needs to assign 20 to each of 3 groups, A, B, and C, for an experiment. Like, great, they captured 60 houseflies. That's awesome. They can capture the flies one at a time when the flies enter a side chamber in the container that is baited with food. Which of the following methods will most likely result in 3 comparable groups of 20 houseflies? All right, label the first 20 flies caught as group A. I'm sorry, the first 20 flies might be faster or hungrier or different because it's the first 20 caught. So I don't want to put the first 20 caught because there might be a difference between each group. So I don't like that one. Write the letters A, B, and C on separate pieces of paper, randomly pick one of the slips, and assign the first 20 flies. Same problem here. The first 20 caught are probably similar for some reason, so I don't like that one either. When each fly is caught, roll a die. If the die shows an even number, the fly is labeled A. If the die is an odd number, the fly is labeled B. That's probably good for A and B, but then the last one is C. Well, for whatever reason, those are the last group caught. Either they're not hungry or they're faster, but they all have a common characteristics. It worked well for A and B, but it doesn't work well for C. So C has a common characteristic that we did not randomize out. Place each fly in its own numbered container, number from 1 to 60, in the order that it was caught. Write the numbers from 1 to 60 on slips of paper, put the slips in a jar and mix. Pick 20 random out of the jar, assign the flies with those numbers to a group. Pick 20 more numbers and assign to B. This is a completely randomized design. This is good randomization. I like this one. This is probably good. All right. E also starts to look good, but we have to look a little bit better at it. When each fly is caught, roll a dice. If the dice shows a 1 or 2, the fly is labeled A. If it shows a 3 or 4, the fly is labeled B. If if it shows a 5 or 6, the fly is labeled C. This is completely randomized. However, we're not assured that we'll have 1/3, 1/3, and 1/3. Although it's randomized, sometimes our percentages get off, so we may not have an even amount, and we were required to have an even amount. So the only way to have an even amount is to put all of the numbers in a hat and draw. The first 20 goes drawn go to one group, the next 20 to the other group, and the last to the third group. So the answer to 35 is in fact D. 36. An experiment has 3 mutually exclusive outcomes. Please remember, if they're mutually exclusive, there's no overlap, there's no intersection. All right? And since we all have probabilities, they cannot be mutually exclusive and independent. Which of the following must be true? They cannot be mutually exclusive and independent unless the probabilities are 0. So that's false. That means 1 is gone, and anything with 1 is gone. Gosh, now we're done. All right, as it turns out. But A and B equals 0. And means intersection, and sure enough, there's no overlap, so that has to equal 0, so that's true. B or C equals B plus C. Well, B or C means union. So B union C is B, probability B plus the probability C minus the intersection. Well, the intersection is 0, so we can just say, oh, it's B plus C. Well, that's also true, and that's what we said. So 36 is D. Number 37. In a study of the weights of college athletes, player weights for a random sample of baseball players and for an independent random sample of hockey players were compared. The computer output below gives the result of a hypothesis test. Baseball player weight equals hockey player weight versus baseball player weight weighs less than hockey player weight. All right. And I just rewrote it down here. Baseball equals hockey. Baseball is less than hockey. And we're talking about weight. We have all this information, and here's a p-value of 0.076. Which of the following is the best conclusion that can be drawn from the analysis? The mean weight of the baseball players is not significantly lower than the weight of hockey players at the 0.05. Well, the p-value of 0.076 is greater than alpha, all right, which means we failed to reject. So that means it's not significantly lower. We failed to reject, all right? And so that right there happens to be my answer. So without going a lot further, the answer to number 37 is A. Moving on to number 38. The game of chance is played, in which X, the number of points scored in each game, has the distribution shown above. Which of the following is true for the sampling distribution of the sum of Y when the game is played twice? Well, anytime you play something twice, you need to make a table. So I can get 0, 0, 0, 1, 0, 2, etc. And the most points I could get is 4, 2, and 2. Well, they said sum, so I need to add them. So 0 and 0. Well, I can get a 0, 0. I can also, which is, that sum to 0. Those sum to 1. These sum to 2. These sum to 3. And these sum to 4. So basically, I can get a 0, 1, 2, 3, and 4, and that gets rid of A, B, and C right away. All right, so how do I get a 0? Well, the probability of getting a 0 on the first roll is 0.3, and the probability of getting it on the second roll is 0.3. 0.3 times 0.3 is 0.09. Well, sure enough, 0.09. So that right there tells me my answer. And if I can check over here, probability of getting a 4. Well, to get a 4, I need a 2 and a 2. And so this is 0.3 times 0.3 is also 0.09. Now I could set up this entire table, but to speed things up, I'm not going to do that. That's enough information for me to believe that it's correct. So 38 is E, okay? Moving on. Number 39. A polling organization asked a random sample of 1,000 registered voters which of two candidates they plan to vote for in an upcoming election. Candidate A is preferred by 400 response. By the way, a random sample. That's one random sample. Candidate B is preferred by 500 respondents, and 100 respondents are undecided. George uses a large confidence interval for two proportions to estimate the difference in the population proportions favoring the two candidates. This is not appropriate. Wait a second. This said two proportions. That means I need two samples. How many samples do I have? I need two independent samples, and it turns out we only have one sample. The two sample proportions were not computed from independent samples. They were not. They all came from a single sample. So that's my problem. I should have had two samples and I only have one. So the problem is I don't have two independent samples. I can't do this test that way. I had two proportions, but I do not have two samples, so it's not possible to do. So 39 is A. All right, number 40 is a regression. Two variables, X and Y, were measured for a random sample of 25 subjects, and two separate regression models were fit to the data. The least squares estimate of the parameters in model A yielded the following residual plot. All right, here's what we need to know. Residual plots must not have a pattern. They must be random and without a pattern. Well, I look at this and I go, oh, there's a definite pattern here. All right. I expect that if I go here, the next value will be higher. But I expect if I go here, the next value will be also higher. But generally speaking, I have some idea. So this one I don't like. I don't like this pattern, this one at all. So model A is appropriate. Anything that says model A is appropriate, I don't like. That gets rid of this one. That gets rid of this one. And that gets rid of that one. So the only one that could be are B and E. All right. So here I have, so this one appears appropriate because it's completely random. If I said, hey, you know what, I got a point here. I don't know if it's going to be above the line or below the line. I don't know where it's going to be. So it's random. All right. I have no prediction that I can on where the value is going to be. So I have log y equals 0.251 plus 0.281x. Well, the very fact that I have a log tells me that X and Y are not linear. X and Y are not linear. But log Y and X are linear because I don't have a pattern. So let's look for that. Model B is appropriate since the relationship between X and Y is linear. X and Y, not linear. Appropriate since the relationship between X and log Y is linear. So this part is linear, but X and Y by itself are not because, excuse me, so 30, I marked that out and I shouldn't. So 40 is E because log Y and X are linear, but X and Y are not. And the reason we know they're not is because we had to put a log in there to get a random pattern. All right, once you put a log in there, it's no longer linear. Or maybe I should say this: X and Y are no longer linear. But log Y and X appear to be linear because the residual plot does not have a pattern. So model B is appropriate. All right, hope that helps and good luck, and I hope you enjoyed the extra credit. All right, thank you.